Okay, good afternoon, everybody. Welcome to the second lecture by Professor Joshua Epstein from New York University. Today we will talk about inverse generative social science, backward to the future. And I'm very happy to have Josh again with his second lecture. Today we also have a special guest from the University of Torino, Professor Pietro Terna, who will discuss the Joshua Epstein's talk. After you got Josh, there will be Pietro commenting, and then there will be plenty of time for questions and answers from you guys here on site and also for you guys connected from home. Josh, the floor is yours.
Okay.
Thank you very much for this second lecture.
Well, thank you. Thank you all for being here. And thank you, Flaminio, for hosting me here in Milan and for your myriad contributions to the field. And Pietro, my old colleague and new friend, I look forward to your commentary. So today's lecture is called Inverse Generative Social Science, Backward to the Future. Last time we talked about generative social science, Agent Zero, and the rational actor. And today, I want to talk about this other idea, inverse generative social science. And this was the title of a couple international workshops and multiple presentations in Milan in 2022, organized by Flaminio. It's also the main title of the lead article in a special guest edited section of JAS on inverse generative social science, also instigated by Flaminio. Along with me, the guest editors of that special issue were Erez Hatna, Matthew Kohler, Ivan Garibay, and Bill Rand. Also, oh, am I blocking everything? Also co-organizers of the workshop. So thanks to everyone. The special issue contains 5 articles, and I'll be talking about these. The titles quickly are Inverse Generative Social Science, Backward to the Future. This is an overarching kind of manifesto article by me. Then article on mixed patterns of segregation, using an evolutionary approach to advance the study of segregation beyond Schelling's original model. Several of us authored that. Then an article using inverse generative social science to explain the empirical data on alcohol use, I should say, in the US. Then a model of flocking. This is the model of actual experiment where students had to make decisions about being altruistic toward others. It's a common pool resources game, and the experimental results are generated in this article. And finally, Laurie Grieg, who's now at DeepMind, contributed an article using inverse generative methods to produce flocking patterns and polarization. So the idea of the journal was to have very diverse applications. All right, so what's in the name? I call the approach inverse generative social science because I'm interested in explaining social phenomena. I have a specific generative notion of explanation in mind, and inverse computational methods, notably evolutionary computing, but other methods, can produce agents, in fact, families of agents, meeting that generative explanatory standard. And I've been thinking about this for quite a while. As an appendix to the article in JAS, I included this memo that I wrote in 1992 to the theoretical group at the Santa Fe Institute. I was the director of the theoretical group, whatever that meant. But it would have included Murray Gell-Mann and Phil Anderson and John Holland and Rob Axtell too, and everyone. And the idea was, I asked this question: is there a set of local rules, that is, rules governing the behavior of individual agents, that over many iterations will generate a crude caricature of, say, the observed international system, a set of coherent societies with internal structures, hierarchical, egalitarian, and dynamics interacting with one another in various cooperative and competitive ways, in an environment affected by and that feeds back on the productive activities of the agents. So I thought core questions might be, what systems of local rules would generate politically egalitarian societies or totalitarian ones? What rule systems might yield social aggregates that are peaceful, others that are warlike and competitive? Can internal stability, revolutions, and so forth be made to emerge from simple rules? And I made this proposal: use genetic algorithms to evolve the rules, to find the rules. And I outlined 5 steps that are actually quite close to the steps we use now in doing inverse generative social science. And I asked the group, what do you think? And I'm not quite sure what they thought at that point, but things have changed a great deal since 1992. And in particular, computing has advanced radically, and now there are related lines of work. Evolutionary model discovery is work by Chataka Gunaratne and Ivan Garibay that is part of the collection. Rule induction is another approach by Bill Rand. Computational abduction, harking back to Charles Sanders Peirce, Murata, and others. Inductive game theory, David Krakauer and others at Santa Fe. I think everyone's getting at related things with diverse goals. Overall, we're looking at a transition from intelligent design to blind evolution of models, all right? And intelligent design. As we talked about last time, I think of the agent model as the principal scientific instrument of generative social science. And to date, agent modeling has been largely the direct intelligent design of completed software agents, fully endowed with rules, intended to collectively generate or grow social phenomena from the bottom up. And Agent Zero, who I introduced last time, is an example of, I'd like to think, intelligent design, but it was in design in any event. And the approach of designing agents and seeing what you can grow has exploded over the last decades with great impact on a huge array of fields, including epidemiology, that I think it's really revolutionized. With the study of violence, archaeology, economics, segregation, ecology, environment, all sorts of things on scales ranging from literally cellular. There are agent-based models of tumor, all sorts of interesting research on cancer, to the literally planetary models. I mean, we built a model with 6.5 billion agents for planetary pandemic flu model. And, you know, again, this is intelligent design. Design the agents and see if you can generate the targets. And that will continue and should continue. But we're talking about standing it on its head. We're talking about, rather than handcrafting completed agents to grow a target, which is sort of the forward problem, we start with the macro target itself and evolve generative micro agents from primitive agent rule constituents and combinators. We don't assemble the agent. What we do is stipulate a set of primitives, constituents, and permissible ways in which they can be combined. And we test the fitness of those and continue evolving until we find agents that can generate the target. So rather than agents as designed inputs, we're actually interested in agents or families of agents as evolved outputs. That is the backward problem, hence my title, Backward to the Future. It's an inverse problem, and tools from AI, evolutionary computation, and related methods can help us solve it. I think it would be a very new use of AI, actually, as we'll discuss. From intelligent design to the blind model maker is obviously a play on Dawkins' famous title. But it's very important to insist at the outset that it's the same explanatory standard. It's the same generative explanatory standard that we're interested in meeting. So inverse generative social science doesn't change the standard, it just finds a way of inventing agents that meet the standard. All right, and what is that? Well, to my mind, to explain a social pattern, wealth distribution, epidemic time series, segregation pattern, what have you, you have to show how the pattern could emerge on time scales of interest to humans in a population of cognitively plausible agents. And the motto, if you like, is, you know, if you didn't grow it, you didn't explain it. But that's a carefully crafted motto. It's a necessary condition for candidacy. I mean, if you can't grow it, you're not a candidate, but not the converse. I mean, there are all sorts of crazy ways you might grow it that aren't at all plausible, by random motion or by all sorts of other things. So it doesn't say any way of growing it is explanatory. It just says if you can't grow it, you're not a candidate. Moreover, and this is relevant to iGSS, I'm not claiming uniqueness. There might be many ways to grow it. All right. And the whole point of inverse generative social science is to evolve families of generative agents. And of course, then we have lots of work to do, like any science where there are competing hypotheses. We need to get new data or design new experiments or find ways to adjudicate between these competing explanatory candidates. But iGSS can give us, families of them that we can work with. It's a very different picture than Nash, Becker, Markov, regression, homogeneous ordinary differential equations. We want to generate the pattern through interactions of cognitively plausible agents. And of course, we're going to argue about what is cognitive plausibility. But, in Agent Zero, I tried to argue that, I think everyone would grant that human behavior certainly involves emotions, deliberations, which are boundedly rational, a la Herb Simon and others, and social interactions between agents that are driven by emotions, boundedly rational, poorly informed, in networks that, in my view, are endogenous. And in Agent Zero, we grow them from the bottom up too. So we talked about Agent Zero and includes those dimensions, but does so formally. I think this is important. I mean, a lot of economists would grant that, yeah, all of that's involved, but we don't know how to model it, so we're sticking with the rational actor. So well, here's a way to actually model it, and let's think about that. Okay, just to say a couple words about those other approaches. Game theory is seen, I think, as the pure mathematics of optimal play in strategic settings. I think that's how Nash saw it. And as such, it's a deep field of math, not purporting to explain human behavior. But in much of social science, political science, some areas of economics and so forth, I think they understand the enterprise. They think to explain a pattern is precisely to furnish a game in which the pattern, some choice of strategies, for example, is the Nash equilibrium or distinguished Nash equilibrium of a game. So how do you explain something? Show me a game in which the thing is a Nash equilibrium. And what that means is simply that if placed in the pattern, if placed in that configuration of strategic choices, no rational agents would unilaterally depart. But that gives no account of how cognitively plausible agents actually attain the pattern or get out of it if it's dominated by other equilibria, or how long either process might take. And of course, what if the pattern isn't an equilibrium at all? So I think this is a very, very limited picture. Similarly, Gary Becker and the entire tradition of optimal control theorists, I think for them, a phenomenon is taken to be explained when it's shown to be an extremal trajectory of an optimal control problem, a la Richard Belbin, Pontryagin, and this great tradition of optimal control. An example is Becker and Murphy's seminal article, A Theory of Rational Addiction. But they posit rational addiction is rational because it optimizes their optimal control problem. But to set up and solve the optimal control problem requires very advanced mathematics. So if the claim is that humans are doing that, it's really untenable on the face of it, and has been robustly challenged, even falsified, by many anomalies documented in many experimental settings, from Herb Simon to Dan Kahneman to Hursky, Slovic, the Elias and Ellsberg conjectures. All of these things are just deep criticisms of this picture of explaining human behavior by showing it to be optimal. Now, Friedman, of course, famously, his gambit was to grant this point and deny imputing these powers to humans, saying that actors behave, well, as if rational. Otherwise, they're selected out. Now, of course, this is problematic for Becker and Murphy, since what they claim to be rational, namely addiction, increases the risk of being selected out by overdoses. But, what I think, rather than a theory of rational addiction, maybe they displayed an irrational addiction to theory. But on examination, Friedman's gamut really reduces to as if anything, random walk, habit, blind imitation that arrives at an optimum. It's as if anything that arrives at the optimum, but then there's no commitment to any cognitive process at all. So why retain the word rational at all right? Moreover, not everything is a choice. Rational choice theory is all about choices. Economics is about choices. And we don't choose everything in the first place. We just certainly don't choose our native tongue, our religion, our ethnic identity, and a lot else. More pertinent, though, as I discussed last time, if I throw a snake in your lap, you don't choose to freeze, calmly considering whether it's a real or rubber snake. You instantly freeze by autonomic neurochemical mechanisms conserved across vertebrate evolution, which we can model. And these so-called survival circuits can induce all sorts of invidious racial, ethnic, religious, gender, and other biases through associative conditioning, which I discussed in detail last time. And again, we may not be conscious of these harmful cognitive dynamics, and modeling can alert people to them and hopefully increase our resistance to them. But scientifically, what we do may be neither rational nor choice. A lot of our behavior isn't chosen, and when it's chosen, it's not rational. So the entire moniker, rational choice, seems doubly misguided to me, or at the very least, restricted to a narrow spectrum of phenomena. So evolving alternatives to the rational actor, formal alternatives, is a central goal of inverse generative social science, to my mind. And I use alternatives in the plural, as I say, because there might be many ways to grow it, many specifications that generate the target, whatever that might be, segregation, histories of ancient civilizations, and we wish to enlist AI, genetic programming, and related approaches in the discovery of these multiple generators. And as I just said, if we have many candidates, we need to figure out how to pick the best one. We need new data or new experiments, and so forth. All right. And just again on these general points, a lot of social scientists are really taught that data are primary. You pull together data sets, you run regressions on them. That's very powerful, very useful. But regression is macro to macro. What is the effect of an aggregate variable on the right-hand side on the left-hand dependent variable on the left-hand side? And that can be great and very important, but we have a different idea of explanation, which is not macro to macro, but micro to macro. And the larger point is that theory can precede and guide data collection. Science doesn't always start with data, and new theories can tell us what data to collect. So, it's true, data sets are great, regression is great, all sorts of methods are very, very powerful, but not all science goes in that way. Sometimes theory precedes data collection and tells people what data to collect. And there are many examples in physics. I mentioned Maxwell's theory, Einstein relativity, that light should bend in a gravitational wave. Eddington had to tromp all over the world to make that measurement. All right. Okay. And as I'm just saying, the new theory might require brand new data and new modes of collection. If the available data were not collected with that specific theoretical motivation, well, it's not surprising that those data may not be suitable to test the new theory. New data might show all of this work, agent zero, all of it to be dead wrong, but I don't think theorists should be cowed by accusations that they haven't validated their theory with data. We'll see. Sometimes the data is in hand, sometimes it's not. One of our workshops was called What AI Can Do for Agent-Based Modeling. And I think it can do a lot, obviously, but it involves a different use of AI. Artificial intelligence is displacing humans, it's augmenting humans, it's defeating humans, but it really isn't explaining them. And I want to enlist it in that enterprise, the generative explanatory enterprise. And just as an example, AlphaZero annihilates humans at chess, but it doesn't illuminate how we play chess. Kasparov defeated IBM's chess player Deep Blue with a brilliant sacrifice, and afterward he was asked, "How did you come up with that?" And he said, "It smelled right." And I think we do a lot of things by smell without the explicit calculation of costs and benefits assumed in the textbook picture of choice. And again, the human fear apparatus is not choice-like, nor entirely conscious, much less rational, but it exhibits regularities that we can crudely represent mathematically in agents like agent zero. I think many economists think if it's not rational, it's not regular, it can't be modeled, it's chaotic, it's you know, and so forth. But things can be regular without being rational. And things like the fear response are very dependable, even though they're not rational, and we can include these in agents, all right? And I think that's more cognitively plausible than the other. All right, so defeating humans doesn't explain them. Another crucial distinction is between explaining and emulating. And here, quickly, not to repeat myself, but the Turing test. Turing considered the question, can machines think, to be too unclear to warrant discussion. And Chomsky wrote a wonderful counter to this that I recommend. And Turing proposed to replace the question, can machines think, with, can we distinguish the computer's responses from those of a human in his imitation game? All right? Whatever else might be gained from the imitation game, a machine's emulation of human output per se doesn't, again, illuminate how, the mechanism by which humans generate the output. So, for example, imagine this imitation game. Behind the screen is a soprano and a perfect recording of that soprano. And let's agree that no human can tell them apart. It passes Turing's imitation game test. But it doesn't tell us anything about how humans vocalize. How is the soprano making sounds? By what mechanisms do humans make sounds? And of course, we blow wind across vocal cords and produces vibrations in the medium that collide with human eardrums, and the sensation of sound occurs. But the Turing test is simply irrelevant to the generative mechanism. The fact that I can emulate the output doesn't tell me anything about humans, which is what we care about, humans. I think the same criticism applies to large language models in many respects. I mean, the fact that a large language model in the actual language applications trained on massive data can spit out grammatical strings tells me nothing about how humans acquire grammar in the first place. With no such training, not by error correction, and long before they have a notable vocabulary at all. We can come back to this as a separate topic, but it's another example of these machines that emulate the output, but don't illuminate the mechanism, all right? And I think similarly, there's a huge world of sort of big data, end of theory people that are in the same boat in a way. I mean, I think the attitude is to understand how the steam engine works, let's start by sampling clouds of emitted steam. Let's collect big steam data. And I can find some model that generates that same big data on steam, but it won't illuminate how steam engines work, right? It might even let me predict steam on Tuesday and steam on Monday, but it doesn't teach me anything about how steam engines work. So again, emulation of the output does not illuminate the generative mechanism. And I think this has been and remains a serious confusion surrounding AI when people talk about these things as being conscious and so forth. They illuminate human cognition. And again, not to belabor it, but I think Markov models are subject to the same criticism. If I claim to have some cognitively plausible micro-mechanism, little m, that generates a target, a final distribution, big M, we're told, you know, well, we don't need any of this because we have Markov transition matrices. We've proved that for any big M, there's a Markov transition matrix T whose equilibrium limit distribution is also M. When I say, well, so what? How does T illuminate the mechanism, little m? Why are the poor to rich transition probabilities, the entries of T, so low in America? T just encodes the social problem. It says it solves with the transition probabilities, but it doesn't tell you the social mechanism that sustains the class structure, for example. Okay, so a lot more to say about what it isn't, the generative explanatory standard, and how inverse generative social science departs from these other approaches. So, having discussed what it isn't, how do you actually do it? With some concrete examples from the special issue. There are concrete steps that are kind of close to what I had in before. You have to stipulate a target. What is it you're actually trying to generate? You have to stipulate the rule constituents. You're going to let evolution combine, or the primitives, rule constituents and primitives, which is very different from numerical parameters. We know a lot about parameter searching. That's not what I'm interested in. I'm interested in rules, natural language expression, saying, if you see a green thing, don't go near it. Something like this, right? It's not a parameter, it's a rule. So you have to tell me what are the rule constituents evolution will be combining. You have to tell me how is it allowed to combine them. Stipulate how the primitives can be combined, the permissible concatenations. For evolution to operate, you have to tell me what is fitness anyway. You have to have a rigorous metric for fitness, compare a model output to some target. You have to tell me, because we want everything to be replicable and explicit, what algorithm you're using exactly. And you have to tell me when the thing stops, okay? The stopping rule. So let's discuss these in turn from the collection, all right? And if anything's unclear, please, all right, good. Okay, so for targets, the target for the Green and Company flocking model was this reference pattern from the famous Boyd's model of Craig Reynolds on the left. All right, and again, they weren't able to send me a movie of how, starting from random positions, it arrives in this pattern by learning rules. And I'll come back to what rules it learned, but it does an impressive job replicating what seems like a pretty complicated target. We'll come back to this. The target for our paper on inverse shelling was, we wanted mixed neighborhoods, not perfectly segregated neighborhoods. So the question is, I mean, we know Schelling's rule famously generates high degrees of segregation when the only consideration is the racial composition of candidate neighborhoods. But we needed to expand the repertoire of primitives to produce mixed neighborhoods, not perfectly segregated one, and we'll come back to that. So the target here was a mixed segregation pattern. The target for the drinking model was the trends in alcohol use in New York State from around 1980 to 2020. So a lot of data for males and females, and those curves both differ from one another. They're not monotonic, although they're not horribly complicated. But the trick was to generate both the male and drinking time series, which is not easy. Green and Company also produced a model in which the targets were polarized opinion dynamics, which again, the reference behavior was this, and the learned behavior is respectively close. And the other group, Lux, Miranda and Company, they were trying to replicate experimental results in a common pool irrigation game played by student subjects. So the issue had many different targets and also very different rule constituents and permissible combinators. Let's talk a little about the Schelling segregation, mixed segregation model. So for any agent A and any candidate neighborhood, Schelling's sole primitive was that the fraction of racial similarity be above some threshold. All right, and we denote that as F race, A agent, I for candidate neighborhood. Right? And since this is the sole constituent of Schelling's model, there are no combinators or anything else. It's just this is the generator. And it generates segregation even for low values. And the larger point that it makes is that, look, you can't infer the individual preferences, which turn out to be mild, from the emergent segregation pattern, which turns out to be strong. Or to put it differently, even mild individual preferences can lead to strong segregation, right? So, even a little racism is a lot, okay? It's like being a little bit pregnant, So for mixed patterns, though, we have to expand the repertoire and add new primitives and combinators. And these are the primordial soup of our exercise, Darwin's warm little pond. Here they are. Schelling's is the fraction of racial similarity that I just discussed, which is this term, fraction of agents who are of the same race as the agent A. But we also said, well, agents might care about the agent neighborhood, the top one. They might care about how far it is from my current location. they might, see how isolated it is from other neighborhoods. I might have a history of movement, and I might have a history of sedentary behavior. It might be part of my personality that I just don't really want to know. And finally, there's the utility of those in the candidate neighborhood. Mean neighborhood satisfaction over all agents occupying those locations in the Moore neighborhood of the site. This is all detail. But the point is, you have to expand the rule constituents to get a different result from showings. And in general, there are several kinds of combinations. There are obviously mathematical ones, like plus, minus, divide, square root, log, take the absolute value. Logical ones, like not and, or if, then, else, things like this. There's recursion. I can nest these things indefinitely, log the log of x. And there are evolutionary operators like mutation. As we'll see in a minute, an agent architecture rule is really a tree. And the trees can mutate at a node, and they can cross over, swapping subtrees and having baby trees whose fitness might be better. All right? For the mixed segregation model, the only admissible combinations were not multiplication and division and nesting, mutation, and crossover. And just as one example of how this is to be thought about. So suppose I have some mathematical surface, some surface in 3-dimensional space as a function of u and v. Z is a function of u and v. All kinds of functional forms between u and v will generate surfaces. And if I start with some random population of functional forms, I'll get a random population of surfaces. But we agree that the fitness of a tree is the proximity of the evolved functional form to some target surface, and we can mutate at a node, cross over with other trees, and produce ever fitter offspring. And for example, a highly fit mathematical form, given this target, is the function u times v plus e to the 4 plus u. And as we evolve them as trees, this is the tree, the genetic program tree representation of that function. And it could mate with another tree and swap a subtree, or mutate at a node and change a plus to a minus, or a 4 to a 19. But the point is, we're generating these trees which encode mappings from primitives to the targets. All right, we'll come back to this. But that's the idea. So for the Schelling model, the second place architecture, we had a very specific definition of fitness, which was Hatton and Benenson's C index, whose maximum is 0.3. And maximum is 1/3. We'll come back to this. But here's the second place rule. This is the agent rule for choosing a new site. And it takes into account all these considerations. Schelling's primitive is, of course, preserved, which is very nice. It's a conserved element across algorithmic evolution, but it also includes distance, age of the neighborhood, and so forth. And they're combined with these answers, with these primitives, divide plus, divide minus, plus, multiplication. And when you put them all together, this is an evolved tree, and you unpack it as a mathematical function. It's this very complicated thing that I think, I don't know if I would have handcrafted that as an intelligent designer. I mean, it seems pretty complicated. That's the second place architecture. Does everybody know what I'm talking about? Yes? I mean, there were earlier trees that were mutated and crossed over to evolve this one that does very well. And it's quite complicated. Here's all the top 10 rules. It's very interesting that the winner is very simple. It's actually the negative of move over Schelling's element, which none of us would have thought of that, even though it's incredibly simple. And it's obvious that fitness falls as we go down this table, but obviously it's not monotonic. The first one is simple. This one is very simple. And they get more and more complicated as you mark around. So in this particular case, we did not find, this is the tree of the fittest rule. which is just moved, minus moved divided by race. It's interesting, GPs can be kind of stupid. And in this case, it included isolation, but it subtracted it and then added it. So all you're left with, it kind of verbose, you know, bloat, I think that's called in the argot literature. And none of us would have guessed that with showing in the denominator, despite its simplicity. And although it's too cute to say that, I'll say it. Inverse generative social science, inverted. Okay. So, you know, in this case, there was no trade-off between rule, complexity, and fitness. There was no monotonic relation at all. But of course, all claims about any relationship between complexity and fitness depend on the fitness metric. So returning to the outline, what were the fitness metrics used in this collection? And for the mixed segregation model, Hatton's C index, published by Hatton and Benenson in 2012, was the measure. And again, the maximum value of the C index for this target clustering level was really 0.33. So the fittest rule is quite fit. Simple as it is. This is the winner again, okay? That was our rule for the segregation model. Our rule for the alcohol work was the plausibility metric from ABC and developed by Adrian Marcus Company not too long ago. Green for both the polarization and flocking used mean square error in both cases. And Miranda and Garabay for the common pool resources game used the normalized square difference between the output and the target. All right, and to ensure that everything is replicable, I included in my article a summary table showing everything that was done for every model. So where's the pointer here? Is that good? So segregation, the target was this, the primitives were these, the combinators were these, the fitness metric was that, the actual evolutionary program developed by Kathak Gunaratne is available here, and the stopping rule was a fixed generation count. We just said you can't go on forever, and we're going to stop you at some. For the flocking model, it was the Boyd's flocking pattern. The agents have to learn there's momentum, separation, alignment with neighbors. The combinators are more elaborate. The fitness metric is simple, mean square error with respect to the reference by every position. You take the output position, compare it to the target position, and take the mean square error of that, and so forth. And all of them, whoops, I'm so sorry. What did I do here? Now I goofed it all completely, didn't I? No, okay, good. Again, I won't go through these in too much more detail, but the point is that for every model, we know exactly what the target is, what the primitives, combinators, fitness, program, and so irrigation, same, alcohol, same. All right, so, you know, obviously good science has to be replicable. So we made sure that everyone was completely explicit about how things were done. All right. All right, so there are still a lot of foundational challenges to the approach, and I wanted to talk about them, having discussed what I think are some, you know, reasonably successful applications. And I think some of these have to do with the way agent modelers are challenged with things, you know. When we give people say, you know, well, I had a successful rule generating the history of the Anasazi civilization. And people say, well, what if you change the rule a little? Do you get the same outcome? Are agent models robust to a small change in the rule? Now, a coherent answer requires us to agree on what we mean by a small change in a rule. We have a lot of ways to define a metric of distance between a model-generated macro pattern, like a wealth distribution, and a real-world target macro pattern, or real wealth distribution. We have all sorts of tests, called Gorf-Smirnov tests, lots of things to adjudicate that. And we also know what we mean by a small change in a numerical parameter. But what do we mean by a small change in rules? A bad answer, a tempting one, is to say the distance between two rules is small if the distance between their generated outputs is small. That's fatal because on that definition, it's impossible to even assert that a small change in rules produced a large change in output, because we've defined that out by saying a small change in rules can only produce a small change in output. When, of course, we're interested in settings where a small change in rules produces a large change in output. Similarly, you can't say output was the same under a huge change in rules, because it's small only if the output is small. All right, so those obvious requirements are precluded by this definition. So we need an independent metric for the domain space of rules and the image space of outputs. And we know how to metrize the latter. But do we have useful ways of metriizing the rule space itself? Well, you could, I mean, what we're asking is, here's a rule, call home, and is that closer to the rule eat a pie than it is to the rule vote for Jones? It just seems nonsensical. But there are lots of ways to do that mathematically, but none accord with any intuition about proximity. None of my intuitions about it. So you could do it by Hamming distance. Rules are always finite strings from some symbol alphabet. So you couldn't code the rules as strings of zeros and ones and compute the Hamming distance between them, the number of bitwise disagreements. But of course, if I encode the rule as all zeros, there are 5 rearrangements, 1 unit from that. And some of those might encode gibberish. And many of these strings might not be grammatical at all, much less synonymous. And so rearrangement conserves Hamming distance, but it doesn't conserve meaning, right? And we care about rules that mean something. And as a side note, this is what bothers me about this power law literature on word frequencies and note frequency, pitch frequencies in literature and music. So there's a lot of literature showing that word frequencies in literature are power law distributed. And I think the literature, I read, kind of invites us to marvel that this is capturing something like great literature and music. Otherwise, you wouldn't use Moby Dick, you'd use the Yellow Pages, right? Or some other phone book or something, right? But when you think about it, every rearrangement of the 200,000 words in Moby Dick has the same frequency distribution, but a lot of those are gibberish, right? Only one in the 200,000 factorial rearrangements is Melville's novel. And 1 over F noise distribution of notes in a Mozart sonata. This is another one. But you get the same distribution of frequencies or pitches if you play Mozart backwards or upside down or random. Okay? So while these rearrangements have the same frequency distribution, they're not works of Western tonal music. So I think there's a degree of self-mystification in this literature about power laws in literature and music. That's just an annoyed aside. Back to metroizing rule space. Hamming is bad. Hamming distance between rules is not good. You could Gödel number them. You could say, take all the symbols and spaces in the formal alphabet and construct a Gödel number for every concatenation that is an agent rule. Okay, and we can go through what Gödel numbering amounts to, but it produces a number for any string. And so the distance between 2 rules could be the difference between their Gödel numbers. But is that actually useful, right? I mean, if the rule is if P, then Q, and another rule is if Q, then P, you know, logicians don't care about the distance between P implies Q and Q implies P, and computer scientists don't care about the distance between programs. And more important for us, neither do our critics, in fact. And if you look at the economists, although they're challenging us about small changes in rules and stability and robustness, the economists don't care about the distance between utility functions, right? I mean, here's 5 standard utility functions, and the agent's rule is max utility, subject to a budget constraint. Budget constraints obviously depend on numerical parameters, but a small change in rules could only mean a small change in the algebraic form of the utility function. I think it's fair to ask us, but it's you know, it's fair to ask us what we mean by a small change, but it's also fair for us to ask them, what if you change the algebraic form of the utility function a little? Is the optimum robust? The algebraic form, the rule, right? I've never seen that even discussed. You know, but to pursue it, you know, would the substitution of the Leontief utility for Cobb-Douglas utility be a small or large change in the rule? Are quasi-linear utilities, Fy is log y, are those closer to perfect substitutes than to constant elasticity of substitution? You know, for a space of functions, we have countless metrics, but I've never seen an economics article or textbook that cares about this at all. So the detractors of agent modeling seem troubled that the ABM can't define robustness to a small change in rules, but completely unaware that they can't either, and it doesn't hamper them in the least. So this criticism just doesn't bother me at all. The real gripe, of course, is that agent modeling, this is with economists and game theorists, that agent modeling is elegant, unified, and general, like utility maximization. But utility maximization really isn't unified if you can choose from an ever-expanding menagerie of utility functions that are available today. From random utilities to prospect theoretic ones to risk averse and its relatives, all exponentially, hyperbolically, however way. If utility maximization, so there's no particular, you know, again, if utility maximization isn't unified in that sense, right? But if it really means only, if utility maximization means simply that for any X star, any X, there's some proper utility function. It's not even, hang on. Right. If all I'm saying is that that I can find an X star that maximizes U. If that's true for any proper utility function, then it really isn't falsifiable. Sid Winter, others have made this point. But if the proposition that agents are maximizing at all, that's been challenged by a host of psychologists, right? I mean, if it's saying, if utility maximization means that for any behavior X star, I can find a utility function maximized by that behavior. So I can always make any behavior utility maximizing by choosing a utility function whose arg max is that behavior, all right? But then it's not falsifiable. And the very proposition that agents are maximizing at all has been challenged by all sorts of experimental work by Simon, Kahn, etc. I think it's too strong to say that rational choice theory is unfalsifiable or already falsified. But I think it's fair to say that the settings to which it applies are less than universal and that the theory is less unified than widely presumed. So we need formal alternatives. One of those is agent zero, but we need to evolve from there as well. Evolved agents might be fitter, but more complicated, in which case there might be a trade. So let's go back to this work. In the case of the alcohol use, did I make that clear in the end after stumbling around so much? For any behavior, there is some utility function maximized by that behavior. That being the case, anything is utility maximized. And then there's the other question, are agents actually maximizing anything? Which is this other critique, right? And we talked about this issue of whether there's a trade-off between fitness and complexity in these rules. And in the Schoen case, there isn't, but in this model, there is. So here the primitives pay off from drinking, autonomy. The descriptive norm is your appraisal of statistical prevalence of the behavior. And we have these other combinators and concatenations. And again, the GP produces this top 1, 2, 3, 4, 5, 6, 7, however many that is. And the most fit one is quite complicated. It involves payoff, nested square roots of things. You know, it's pretty ugly. The clean one is very clean at the bottom payoff, but it isn't very fit. So here's the trade-off for that. All right. You can have very low error at the cost of very low comprehensibility. Right? So there's a trade-off there. We went ahead and penalized the rules for complexity. You can include the penalty inside the fitness function. So we penalized it for rule complexity, the number of nodes in the tree, biasing selection toward more human interpretable rules. Again, if we're just about black box prediction, we don't care. Like a lot of the LLMs and machine learning and other things don't care. But if we care about generative explanation and cognitive plausibility, we do care. And again, in the Generative paper, we found that the winning rule was very simple. So we don't think there's a general trade-off between fitness and complexity. It occurs in some cases and doesn't occur in others. Another interesting behavior in these models is the presence of punctuated equilibrium. It illustrates that evolutionary learning is not smooth, but occurs in jumps as new constituents are added. So from the flocking model, it starts again with this random configuration, and then it learns alignment and separation. Then it learns how to normalize those. It learns how to cohere, but not smash into other people. And so you get this growth in the rules fitness, but it doesn't occur smoothly. It occurs in jumps as they learn these new primitives and add them to the rule. Same, and it's very interesting that punctuated equilibrium occurs in multiple runs, but for stochastic reasons, the jumps might occur at different stages in the evolutionary process. All right, the flocking model. Same for the alcohol model. We did gain in fitness rather than loss in error, so it rises to the right instead of falling to the left. But it again exhibits punctuated equilibrium. All right. So these are all very interesting features, and it exhibits conserved elements. You know, as I say, we can't usefully metrize rule space, but we can't have neighborhoods of rules. I can't say all rules within distance d of one another, but I can evolve phylum rules beginning completely from scratch, or from a parent model like Schelling's, which we did. You disassemble the original model, put constituents plus new constituents in a primal soup, evolve new fit rules for an existing problem or for a new problem. And as a nice example of this, Chataka Gunaratne and Ivan Garibay evolved new rules for the ancient Anasazi model that you might be familiar with that do better than our original model that Rob and we published in PNAS. It's more complex, but not terribly more complex, and it's better. So I think, great, that's progress. I'd like to do the same thing with Agent Zero and all sorts of other things, right? I'm not wedded to any model. I'm just wedded to the method, okay? So major goal is to evolve cognitive plausible alternatives to the rational actor. I think Agent Zero is a defensible start in a couple respects. I'm going to go a little quicker now, I think. It's a departure from the rational actor first, in that it's directed at questions rational choice just avers, it doesn't apply. Rational choice doesn't concern formation of political, economic, and other preferences. And George Stigler's famous statement was, we don't argue about tastes. Tastes are not something we think they are what they are. We're not interested in how they happen. And contemporary rational choice theorists really deny that theory has anything to say about how people acquire baseless fears, genocidal hatreds, erroneous beliefs, logically inconsistent patterns of thought, self-injurious preferences, or anything. For a really clear, brave, unadapted statement, Herb Gintis in 2018 published, the rational choice model expresses, but does not explain individual preferences. The rational actor just maximizes utility, whatever preferences those he might have, right? If he prefers ethnic purity to less, it might be perfectly rational in the Orthodox theory for him to join an ethnic cleansing, right? It doesn't make any statement about the preferences themselves. It just says, given the preferences, you maximize. But we care about the preferences. We care about what cognitive or social processes actually produce baseless fears, murderous disposition. How do those happen? And the rational choice theorist, Agent Zero, gives us some clue about how those might happen. And the rational choice theorist tells us, you know, we don't care, look elsewhere. Okay, fine. But we do care, all right? And so we're interested in how genocidal utility functions happen through combinations of unconscious emotions, animal spirits like fear, errors in conscious appraisals of risks, amplified in networks of other emotionally driven, fully informed, typically hobbled fears. And Agent Zero tries to do that in a simple, provisional, crude, but perhaps illuminating way. Rational choice theorists will just simply say the question lies outside the ambit of rational choice. Okay, but we're interested in that, in those things. And Agent Zero at least posits specific, perhaps falsifiable, affective, deliberative, and social modules grounded in cognitive neurosciences. And the choices are not ad hoc. Another claim about agent-based modeling is, well, you just make up things, it's all ad hoc. Well, this wasn't ad hoc. It's based on fear of conformity and so forth, and well-established departures from perfect decision making, a la common scientific analysis. So it's not at all. I would say that the fairly parsimonious way at it is directed at cognitive questions that are explicitly disavowed by rational choice. So one sense is that they're just not interested in our questions. But where the two, but where the two concerns overlap in areas that are within the scope of rational choice, agent zero does violate a central canon of it. In choosing a level of activity, rational actors set marginal benefit equal to marginal cost. I reviewed this very quickly at long 10. And agent zero doesn't know that, doesn't do that, and he knows that he doesn't. All right. And I'm not going to review this because I think I want to hear what Pietro has to say. But as noted in the earlier lecture, you can interpret agent zero as a kind of disposition minimizer, and he retaliates on sites to reduce his disposition to attack. All right, and agent zero knows that it's irrational to continue. So I have this little picture that I'll just look at again. These are 3 agent zeros occupying a foreign land in which some region is insurgent. They're being attacked, they're being ambushed by yellow inhabitants. And when they're attacked, the site turns orange. And if they're over their threshold, they retaliate, destroying sites. But the destruction continues long after there's no threat. So their internal estimate of the probability of attack goes to 0, but they continue killing because their affect hasn't decayed. All right, we'll come back to this, or not. And just as a final point, this is a departure from a lot of the dual process literature. The idea that humans have different competing modules isn't new. There's a whole history of this. Stanovich and West introduced the terminology of system 1 and system 2 that Kahneman so nicely uses in his best-selling book, Thinking Fast and Slow. But there are no equations in that literature. And in agent zero, there are equations. The effective deliberative modules are mathematical. So I don't claim any sort of isomorphism between Kahneman's system picture and mine. But in some settings, the analogy is interesting. So as discussed earlier, in the classic case of a snake, fear acquisition is faster than the conscious dispassionate appraisal of the threat, as we talked about last. In that case, in acquiring fears on the way up, as it is, system 1 is faster than system 2, but on the way down, in expunging fears, the reverse may attain, just as we showed here. The system 1, the affective system, is actually the slowpoke, not the faster. In expunging fears, the PTSD being the obvious extreme case. Okay, so mine is really a kind of triple process model, where the affect system can be the slow one. And I would say, at least in my model, there's no uniform relationship between the speeds of the affective and deliberative modules. And we also have a social, making it a kind of triple plus model, if you will. All right. The goal in agent zero was not to get the modules finished, but to get the synthesis started. And what I wrote was, whether this particular agent or some distant progeny yet to emerge, I believe this broad family tree of individuals, each capable of emotional learning, bounded rationality, and social connection, is well worth developing. And today I would say well worth evolving with inverse generative social science. A lot of people, when I give this talk, they say, well, isn't iGSS the end of theory? And I would say no, but it changes the locus of theory from the completed agent to agent constituents, rules, modules, building blocks. And these have to meet defensible notions of cognitive plausibility, and all of that will require human judgment, but at a different level about primitives, concatenations, modules. And I would say, this work obviously can depart from some humans' designed model, as in the shown case, or from agent zero. I'm perfectly happy to disassemble agent zero and add other constituents and see if we generate, this agent or something very different. I'll talk about agent zero cognitive epidemiology next time, but we're also doing agent zero addiction modeling, where, unlike Becker and Murphy, we do include as a module some actual neurobiology of addiction. All right, so that's a mouthful. I'm happy to have criticisms, comments. Thank you, and I'd love to hear, thank you so much. I'm honored and thankful to hear Pietro's comments.
Thank you, John. I'd like to invite Pietro. Just do like that. There. God, share some.
Oh, yeah,
Moves. Here. Okay.
Control N.
Yeah.
Many thanks.
It's visible.
Control L is full screen.
Good afternoon, everybody. Let me first of all thanks Flaminio for the huge honor of being here to discuss Professor Epstein's wonderful lecture. I start from the book. Doesn't work.
Click on the.
Oh, I start from the Epstein and Axel about growing artificial societies. Let's see the key dates, my key dates. I started building agent-based model in the beginning of the 90s, something maybe at the end of the 80s. And I was programming in plain C, no object-oriented facility there, very complicated. And I was in the dark, no one to interact. You have to understand that the internet was not there. So it was very difficult to interact from people far from your country. Then 2 dates changing my life. The first one is the novelties that in the middle of the 90s, exactly in 1994, with the alpha version, very dangerous because they forgot a deal star.star instruction in a script, deleting your machine. So quite dangerous, but it was the alpha version. For the Santa Fe Institute, we had the first unified tool to develop strong agent-based model with a lot of agents, named SWORD. A wonderful achievement, and the key date, for it. But the second key date was the book Growing Artificial Society, demonstrating that it was possible to analyze a very complicated society with parsimonious tools, because there they limited the number of rules, the number of artifacts. Simply one artifact, sugar, and the population fighting, socializing, creating new tools, and so on to achieve the results. Wonderful, very encouraging for me and for other lot of people in the world. This is my review, a bit late because the review is 2001, but I was looking for a reason to be the reviewer of so important work for me. Know that jazz was at year 4, so we were quite far in the beginning.
Far from me.
You were young.
I was, yeah.
Still young, come on.
Thank you very much.
Why the discussion? To reply to a wrong criticism from a not important journal, but the criticism was very strong, and for me, it was the opposite of the achievements of this book. Exactly the capability of describing in a non-exact way a society. leaving a lot of possibilities, of nuances in your description was the interesting part of the result, not the need of an exact, perfect, controlled result. So I wrote the review. And I was also wrong, because I was advocating the possibility of having a reverse engineering of the models, but fearing that it was possible at this moment and in the future. And I was wrong. First of all, George was writing his note to EDNAP in the appendix of the article is for showing us in 1992, so 10 years before my guess. So I was only not aware of the possibilities. Anyway, this is another step, very important. In the same review, I was proposing an idea of mine. And this idea is always in my mind when I create my models, but not always it is easy to implement it. The idea is that in a model we have an environment with agents in a different ways linked to the environment. Agents have a rule master, so a system of rules driving their action. This is not inverse generative, it's generative, direct generative. But we can try to modify the way the agent behaves, having the activity of a rule maker. This is a rule master, this is a rule maker modifying the rule while the simulation is running. This is the key idea. You need a lot of computational power, sure. You have to stop the simulation and maybe run a genetic algorithm, run a genetic algorithm here to modify the rule. It is a simple idea, very difficult to be implemented. But anyway, this was my idea at the beginning of the new century. Now, a wonderful plot from the new book of the Informer, just published. The author is a graphic designer named David McIntosh. And here you have the zero intelligence gate, not the agent zero, the zero intelligence agent. In the beginning, or no, in the end of the 90s, we had a lot of work in the stock market with zero intelligence agent, creating extraordinary series. Then we stopped this field because it was not evolving novelties. Anyway, these agents are only randomly behaving. Here we have the impossible rationality gate. This is outside the reality. And then within, we have the wilderness of rationality with a lot of strange movement and emergencies. Maybe the drama is actually here, the drama for the modeler. But the story starts from a very sound perspective wrote by Keynes. If you read this quotation, and I owe the discovery to a colleague of mine, Professor Marchionati of Torino, you see that from the brain, for the intelligence of a physicist like Professor Planck, the economy is difficult for the amalgam of logic and intuition and the wide knowledge of fact, master of which are not precise. This is exactly what we can obtain with inverse generative social science, because we have an amalgam of very difficult facts, data, elements, and we try to have the emergence from there of a description with a set of rules, very, very interesting. The sequence of the possible rules with sequence of rules of the behavior of the agent. So the future, I guess, is there, is in the possibility of using tools to evolve models like those introduced by Professor Epstein. From the Cosa fundamental book with genetic programming using expression in a Lisp notation. Lisp is a fundamental logical structure. Lisp means list processor. And in Lisp, anything is a rule and can be modified by other rules. So it's a wonderful tool. Now we have also very modern engines, like those are created in TensorFlow by Google. Not easy to be used, sure. But anyway, close to the new deep learning techniques. So very interesting to be analyzed at this point. Or we can simply use direct genetic algorithms in a scheme like my environment rule agents, because now we have a lot of computational power. I perform some computing, was not there when I started doing this kind of things. Now we have it. And we can also interact with tools allowing us to distribute our agents in a multi-core way in agent-based simulation with direct interaction. Pay attention, this is very important. Direct interaction among agents running on different cores. And is a great novelty. Not so simple to be implemented, but with my colleague Eleonora, who is there, we demonstrate, Eleonora, we demonstrated that it is possible. Not easy, but possible. We have a large model about that, and we will write a short note for the letters of jazz, not jazz, but what?
Profs.
Floss.
Profs.
Rofas. A short letter with an example demonstrating it is possible. It is not a scientific achievement, but is a strong achievement after 6 months of fighting with the problem. It works. And Repast is a very interesting tool in the new Python version to do that. And here you have a website of this not simple, but very powerful tool. Or, and then just close to conclude, we can try to use tricks. Tricks in science are a lot. And my trick is to put in a model a virtual planner. The virtual planner can, as an example, choose the best strategy in vaccination. And then remember, it's not trivial, because no one started vaccinating workers, but fragile people, fragile workers. No, all the workers, because they are joining a lot of people and their families. And in the simulation, if we start vaccinating due to the choice of the genetic algorithm workers, the effect on the wave of the future, or the future wave of the epidemic spreading is evident. It's very, very interesting. Just a short hope that of using in our models large language models not to simulate natural intelligence. This is completely wrong.
Yes.
But to create messages among agents.
Agreed.
And this is a wonderful paper. I invite you to look at it. These agents living in this space are able to coordinate and to decide actions because they, quotation mark, understand what other people are saying. Maybe in the future, we will try to add also this. The last slide is a QR code to have all the links. Oh, I am concluding, as you see above, but let me have a short dream. For me, this quotation for Leibniz is very, very important. To avoid fighting, while we can substitute for the thing with calculations. Yeah, but for us, it's not calculate, it's simulate with inverse generative science. Sure. So, thanks, Josh, for your past as a terrific pioneer and for continuing to be extraordinary and extraordinary pioneer today. Many thanks.
Thank you.
So, John, would you like to comment on Pietro's?
No, I agree with all of it. I think it's great.
Many thanks.
No, I think it's a wonderful book. I congratulate your colleague on their recent work. No, I think we're birds of a feather.
That's good. So we have some time.
Honored. Very honored. Certainly agree on the science, but also deeply honored. Feelings are entirely mutual.
Okay.
Excellent. So, thank you, Pietro, for this very touching and passionate type comment. I know how much this event here matters for you. So we have time for questions and comments, and also for you guys online. Let me say that I can do that. Try to do that so that we can also change these. So, any question, any comments? Okay, don't touch anything. So any question? Yes, please, Eduardo. Yeah.
So, thanks for the talk again, Joshua.
Want to ask any question from home? In just raise your hand and or write down the question in the chat. We'll read the question here.
So another economics-related question. Then, in the history of economics, there's this big micro foundations problem. Right? So the place where economics flounder, depending on which story you read, or maybe the failure of micro foundations led to game theory. It's a big area. And then on heterodox economics, then there's another theme of the macro foundations of microeconomics. Right? You start with the macro target pattern. You have to discover rules, agent rules, or patterns that are micro patterns that are compatible with that previously identified macro pattern, which to me is reminiscent of what you are proposing with iGSS. So just as an open-ended question, like if you've seen anything like that in the literature, is it worth pursuing this type of line of inquiry?
Well, yes, certainly it's worth pursuing. I mean, people like Blake LeBaron, for example, and Kars Ohms are pushing this very hard, and Rob Axtell also, John Giancopoulos. It's not exactly inverse generative using GAs and the rest, but I mean, the idea is to provide micro specifications that do generate patterns, including abrupt patterns like housing crashes, financial panics, and other sorts of things. So, excuse me, just getting over a bug. So I think it's a very fertile line of work. There's a lot of new data, which is very helpful. And I'm very interested, I'm actually pursuing some work on financial panics with Agent Zero, because, the way I think of it is Agent Zero is fear inspired and fear is contagious. And fear requires surprise, it turns out. And surprise is the violation of expectations. So if you're in a speculative bubble, expectations are inflated, they burst, and you get a spike that's contagious. And I think we can do some simple modeling of financial contagions and panics and crashes using the general approach. So it's not a very good answer, but I think it's all very important. I would just, some people use the word micro foundations to refer to the representative agent, which I think is really, really way off. It's just, there's Alan Kerman's famous article, whom or what does the representative agent represent? And I think that's the dead end, to be honest. But I think there's a lot of work along these lines with these guys that are very interesting.
Okay, thank you, Francesco.
Thank you, Josh, for the inspiring talk. Was wondering whether you have thought about metrizing this space of rules that this algorithm generate, or if this makes sense at all.
You know, I think it's a very deep, I think it's one of the really sort of Hilbert problems, the whole approach. You know, what do we mean by the stability of one of these models? And I mean, in mathematics, we have this idea of structural stability, which is, you know, that the preservation of the phase portrait to changes in the algebraic functional form, you know, the vector field, things like this, where you do change the functional form, but still retain the same, you know, the equilibria and the flows are preserved under those deformations. And I just think we have deep work to do on sort of what would be the analog of that in agent-based modeling, and what do we mean if I change an English language rule, like look around for the best sugar and move toward it. What is that? What's close to? What does that mean to be close to that? Does it mean look around less far? Does it mean look around for the worst sugar? Does it mean where are we in thinking about the proximity of one rule to another? And without some notion of proximity, certainly the classical idea of, you know, within this neighborhood of X values, I get the same behavior. I don't know how to do that with agent modeling, but I think it's very interesting that we can show phyla of rules, if not neighborhoods. And I think that's very interesting that the Schelling rule is conserved through algorithmic evolution. And other work has shown this to you know, shown the same sort of property. So the short answer is I worked very hard to think about that, and I'm not satisfied with any of the answers I could come up with. And I'm sort of left with the feeling that it may not, and I say the economists don't even ask the question, and they don't know what it means to be near the cognitive utility function algebraically, right? It doesn't hamper their work. So I don't know how to answer it. I'm not sure it ends up being terribly important. I think phyla rules are very interesting. And we can say within whole phylogenetic branches, you get the same behavior. So I think that might be a new type of stability to think about. But I welcome you to think about it and help sort that out. I think it's a very foundational and demanding question, honestly. And other fields, let me just say, other fields don't care about it either. I mean, computer science doesn't care if one program is near another program, right?
I will follow this question in the sense that given your focus on cognitive plausibility of agent behavior, I would say that suppose that you have a bunch of rules which fit the distribution, like the mixed segregation patterns and so on. Okay, you might have a criterion to try to, you know, adjudicate between a number of maybe short number of rules which maybe are very close to fit,
Right.
which could be maybe, as you said, simplicity. I mean, how much cognitively computationally demanding are. So this is where you still see the value of the, the exercise of adjudicating rules according to some cognitive plausibility. Which, but are also you interested to understand how we can methodologically maybe validate? Maybe you've set up an experiment with humans who have at some point to adjudicate or rank this kind of plausibility. Also, rules would make sense from the point of view of a human, or there could be an extension or another way around in the sense that this, when you have rules which are probably plausible for generating that kind of a reality, you may also understand what other realities they can generate at the same time, maybe, or similar type of phenomena like segregations and education. Or do you see any potential in that?
Yeah, I think that's very fertile. I mean, as I was saying, I think we have to be creative in designing experiments and collecting data that let us tease out, you know, which of these models really does seem like a plausible representation of human cognitive, you know, cognitive behavior. I also think there's a very rich literature in psychology with Kahneman and Tversky and these well-established departures from canonical rationality some of which are very simple, that we can put into agent models or make constituents of models. I mean, I'm working closely with Paul Slovic on this cognitive epidemiology that I'll talk about next time, where there's a phenomenon that's very well established called psychic numbing that derives from this famous Weber-Fechner law, where, you know, we don't actually register I mean, if I hand you a 10-pound weight, you'll say, well, that's a substantial difference from zero. But if you're already holding a 90-pound weight and I add 10 pounds, you don't notice anything. So that you don't register the absolute change in weight. You register the fractional weight, the change. It's really the log of the weight that you register. And when you put that into an epidemic model and say, look, people don't notice that 2 million people died of COVID, they notice some very compressed log Weber-Fechner compression of that. Those are all low-hanging fruit to put in as constituents, and they're well established. So I think we should be mining the literature, the serious scientific literature on cognitive biases and the rest, and include those in the primordial soup of constituents, because they do have credibility on their own. And one step I think is to really make better use of the existing experimental cognitive science. But your point is very well taken. And of course, I think this is a huge, very, very important step, and one that we're at the start of this.
Okay, thank you. We also have a question, Shiva from online. I want to ask if to apply this method will be NetLab or Python. So it also opened the questions about which are the best or more appropriate type of environment in which to perform this, inverse generative exercises.
Well, I mean, again, excuse me. For example, in the paper, I mean, Rory Grieg and his group have specialized systems at Google and DeepMind and the rest. Shadika Gunaratne wrote in that logo an evolutionary model discovery code. But I don't think there's any, I mean, again, I don't think there's an industry standard for doing this. And I think people in the collection did it in very different ways. Some people using Python, some people in that logo, some people repassed, as Pietro mentioned. Some people, Shadika's got his own evolutionary model discovery system. I think there's a whole ecosystem of softwares and platforms that people are using to do this. And probably people are still using Lisp and other methods. So I don't have a simple answer.
No simple answer.
There's no simple answer.
In life.
In life.
By definition, yeah.
In artificial life as in life.
I love that. So I guess that
Repast contains also a module for genetic algorithms. So the possibilities are large.
So, any other questions? Also, you guys from home? Yeah, thank you. Yeah. Marco, yes, please.
A question for Professor Terna, but first of all, thanks both Professor Epstein and Terna for the very inspiring presentation. So a short question about the idea on the large language models you proposed. The first one, which is, I guess it's the very first, is, did you already try it? And the second one, it's like in the direction of your idea. It came to my mind something like the works from Brian Uzzi about the communication between traders and investors. I mean, I see these two things very close, and it would be very interesting to apply these large language models to settings like this one to see what we get, basically. So, thanks.
This direction is very interesting. Imagine it to evolve a specific, not so large, but medium language model with the information about a system of decision where the words that a neural network is linking the model are related to the subject of your research. It would be very interesting to see if the agents are finding new way of operating. We are building currently a production model In a production model, a lot of decisions are there. And to decide, you have also to agree with partner, with the clients and so on. So it is a completely new field. It's not so simple, but in this paper is probably.
Thanks.
Okay, any other question, comment, request?
Another question.
Okay, so, okay, let me just read my, let's see. If you want to pose your question yourself, don't feel.
Yeah, please.
Okay, so he, Songming was suggesting, his or her,
Thanks.
get up. Okay, there's framework here, the genetic algorithm. To see how to include that. Okay, that could be brilliant. Yeah, that's very.
Maybe I'm forward.
Okay. Okay, again for all melody.
Many thanks.
Yeah.
Good.
Hello, if I may.
Oh yes, please. Oh yeah, good to see you. Ciao. Hey.
Hello. My name is Song Min. I work in Fraunhofer Institute in Germany, but actually I'm now in China, so it's deep dive. But I'm very happy to join the lecture today. I was first in the first lecture, and then today's lecture. I also joined the next one. I just want to mention my framework because I think the inverse generative framework is quite interesting. And what I did in my PhD was to train the agents with genetic algorithm, but to maximize some accumulated profit or utility. It's not minimizing some distance, but I think it's a bit similar to trained agents to reach some macro level validity or yeah. So I think I will try to include this feature to minimize the distance in this framework and then play with some models following these ideas. Thanks a lot.
So
Good. Thank you. We can't wait to see your result of this effort. Yeah.
Thank you.
Thank you for contributing. Any other?
Yeah.
Yeah.
So a follow-up question on this issue of the representative agent.
Yeah.
On one of these examples from the special issue that you mentioned, the agents that are evoked or grown, how close or far are they from a representative agent, or how heterogeneous are they?
Well, again, in that particular issue, I don't think any of the articles were really about market behavior, or firms or.
Or more generally, do the agents look like each other a lot or not that much?
How heterogeneous are they?
Yeah.
Yeah. Now, I think in the issue, we were really looking for single rules that generate. So a huge move is to to make those more heterogeneous. We ranked individual rules and assumed that everybody adopted.
Right.
So, right, you're exactly right. I mean, the whole point is really that they're heterogeneous agents. So we need to work on that as well. We probably, and there are a lot of ways to think about that, is that there might be some rules that you're equipped with some distribution over rules and you draw from the distribution. So that's.
Okay. If we don't have any other questions from the audience, I take the chance to send my greetings to Juliette. I see you appreciate my friend. So I would like to thank Josh and Pietro for this brilliant discussions about the future of ABM. So that's a lot of hopes and energy for that. So I'd like to remind you that we have another lecture by Professor Epstein next Tuesday on cognitive epidemiology with Ilaria Capo as discussant. And I'd like to thank you very much and see you next time.
Thank you all.